Why don't powered parachutes use reserve parachutes? Skydivers do, Paragliders do, Ultralights do. Even certified airplanes like the Cirrus SR22 use them. So why don't we? My name is Roy Beiswinger. I've been training powered parachute pilots since 1993, and I'm a designated pilot examiner and Gold SEAL flight instructor. This is one of the most common questions I get from prospective pilots. In this video, we're going to break down exactly what reserve parachutes are designed to solve, and whether those problems actually apply to powered parachutes. Because a reserve parachute isn't just extra safety. It's a solution to a specific failure mode. And if you don't have that failure mode, the solution may not make sense. So let's walk through it carefully. Let's start with skydivers. A skydiver's main canopy is packed tightly into a small container. It has to deploy quickly and clearly at relatively high speed. Most of the time, it works perfectly, but sometimes it doesn't. Sometimes the canopy opens with severe line twists. Sometimes it spins violently. Sometimes it fails to inflate properly at all. When that happens, the skydiver cuts away the main and deploys the reserve. Skydiving reserves are mandatory. They're inspected and repacked every 180 days by FAA certified riggers. They're built to extremely high reliability standards because they absolutely have to work. Now here's the key question. Do powered parachutes have that same problem? No. We don't pack our wing into a container and deploy it at speed in the air. We lay it out on the ground. We inflate it on the ground. We watch it inflate. If something doesn't look right, we stop. If a launch is blown, we're still on the runway. We reset and do it again. So the primary failure mode that skydiving reserves solve, packed deployment failure, simply does not exist in normal powered parachute operations. That's a completely different scenario. Now let's look at conventional ultralights. After surviving a hang gliding accident, Boris Popov went on to found Ballistic Recovery Systems, or as it's known in the trade, BRS. The idea was straightforward. If the structure fails in the air, deploy a parachute and bring the whole aircraft down. Early fixed-wing ultralights were extremely lightweight. Some operated very close to structural margins. If you had a structural failure, there wasn't much you could do. A ballistic parachute made sense, and those systems have saved lives. But again, we have to ask the same question. Is structural airframe failure a common issue in powered parachutes? Not really. Powered parachutes don't have rigid, cantilevered wings sticking out from a fuselage carrying bending loads. The lift loads are distributed through suspension lines into a central airframe. There's significant weight savings in not having a rigid wing structure. Because of that, the airframe itself can be built robustly. Most powered parachute airframes are, frankly, overbuilt. The structural failure problem that ballistic systems were originally designed to address in ultralights just isn't something we see in powered parachutes. Different structure, different load path, different risk profile. Next is paragliders. Paragliders use reserves for a different reason, efficiency. Modern paragliders are thin, high aspect ratio wings designed to maximize glide performance. But high efficiency often comes with reduced stability. High aspect ratio paraglider wings can collapse in turbulence. They can experience asymmetric deflations. They can enter into deep spirals and become difficult to recover from. So paraglider pilots carry reserves because if the wing becomes uncontrollable at altitude, the reserve provides a controlled descent. Now compare that to a powered parachute. Our wings are lower aspect ratio, thicker, heavier loaded because we're carrying a substantial cart and engine underneath. They're designed for stability under power, not maximum glide efficiency. That difference matters. The collapse behavior of a high-performance paraglider is not the same as the behavior of a powered parachute canopy operating within its normal envelope. Again, different problem. Now let's consider conventional airplanes. Aircraft like the Cirrus SR22 use whole aircraft parachute systems. Why? Because airplanes move fast. If you lose an engine over rough terrain, forward impact speed can be significant. You may not have a suitable landing site. A ballistic parachute converts forward motion into a more vertical descent. It's not perfect, and the aircraft is usually damaged, but it can reduce injury to the occupants. Now think about a powered parachute engine failure. We are already under a parachute. We are already descending at a relatively low vertical speed. We simply glide to a landing and flare. There is no high-speed forward crash dynamic to convert. We are already in the configuration that other aircraft deploy a parachute to achieve. That's a major distinction. Finally, EVTOL aircraft. Many electric vertical takeoff and landing aircraft include ballistic systems because, in some designs, if you lose total power, you don't glide. There's no auto rotation. There's no conventional glide path. A parachute becomes the last line of defense. But powered parachutes? We are gliders with engines attached. Remove the engine, and we're still gliding. When you look at the 5 major problems reserves are designed to solve: pack deployment failure, structural airframe failure, collapse instability, high-speed engine outlanding, or total loss of glide capability, powered parachutes simply don't share those failure modes. And that's why you don't commonly see reserve parachutes installed on them. In 3 decades of powered parachute instruction, I can't remember ever seeing one equipped with a reserve. Now, is it a never? No. If someone is doing aggressive aerobatics and repeatedly loading the wing beyond normal limits, fabric fatigue can occur. I personally know multiple cases where wings failed later during normal flight after being overstressed earlier. If you operate outside the standard envelope, additional redundancy becomes more defensible. Some countries may require reserves in certain classifications. An insurance company could require one. Highly modified or experimental aircraft might justify it. So it isn't just black and white. But we also have to talk about the trade-offs. Powered parachutes typically operate at relatively low altitudes. Ballistic systems require time and altitude to deploy and stabilize. We also cannot cut away our primary canopy like a skydiver can. If you deploy a second parachute without neutralizing the first, you risk entanglement. 2 wings interfering with each other can render both of them nearly useless. And ballistic systems contain explosive charges. If there's an accident and the system hasn't deployed, that charge becomes a hazard for first responders. Finally, installation requires real engineering. Rocket trajectory, line length, structural reinforcement. It's not just add another parachute and you're safer. You have to understand what problem you're trying to solve. Reserve parachutes are designed to solve very specific problems in aviation, and most of those problems simply don't apply to normal powered parachute operations. Powered parachutes begin flight under an inflated wing. We're already gliding. Our structures are robust. Engine failure is not catastrophic in the same way it is for many other aircraft. More equipment does not automatically mean more safety. Understanding your aircraft does. If you're serious about learning to fly a powered parachute and you want structured one-on-one training, I offer 2-week courses in both the Midwest and in Florida. Most of my students come to me after months of research. If that's you, you're in the right place. Classes are limited and they do fill. If you've been thinking about it, visit the link in the description at easyflight.com and take a look at the upcoming schedule. And if you appreciate clear, no-nonsense discussions about powered parachutes, go ahead and like and subscribe. Thanks so much for watching. Blue skies.